Hello everyone. So in this video, we're going to see Bitcoin's consensus algorithm with your two favorite characters in play, that is your Alice and your Bob. So let's just see how it goes. So when Alice wants to pay Bob, she creates a transaction and broadcasts it to all of the nodes. So every transaction in blockchain, it has to start with a broadcast. So here, Alice payment request doesn't go to a bank, doesn't go to any central authority. Instead, it goes to the entire network, to every node that is participating in your network. Next, it says each node is constantly listening to the network and collecting a list of transactions not yet inserted into the blockchain. So, all your nodes are kept on the standby. They're just listening to all the transactions that are happening and taking an account of all of these. So it's just like I'm gathering all the pending transactions until they're ready to be validated. Then at some point, one of these nodes is chosen randomly to propose the next block. It will put in the new block, a bunch of transactions, and add it to the blockchain. So now you have to take a decision. A random node will become the block proposer and it will package all the transactions that it has gathered into a block and suggest it as the next addition into your blockchain, right? To be appended into your blockchain. Then this node can also be honest, can also be malicious, can try to insert some invalid transactions. For example, it could insert a transaction with a non-valid signature or with the coins already spent. With coins already spent, I mean double spending. We'll see more on it in the next upcoming slides. So let's just see. So here's the risk. Now this node that you've chose, that has been randomly chosen as the proposer, could actually be an honest node, giving you all the actual transactions that have taken place, but it can also be a malicious node which can try to sneak in fraud, fake signatures, double spending attacks, double spending coins. Now the other nodes, right? The other nodes will accept this block or can reject it by either including the hash of this latest block in the next block or ignoring it. So now what, the network is going to act as the judge because we don't have any central authority. So the entire network, the network is going to act as the judge. If nodes see this block is valid, they're going to build upon it. When they build upon it, that means they're going to take this hash and include it in the next block that they're going to build, right? Because they are again going to be on a again going to be a standby to gather the transactions that are happening. So if they think this block that has been proposed by this particular node, it is actually honest, they're going to take this block, they're going to take the hash of this block and and keep this in their upcoming block because they can be chosen as the block proposer next time. But if they think that okay, this node is invalid, the block that this node has proposed is actually invalid, they can just ignore it, right? So what happens? The block is accepted only if all the transactions in it are valid. So they're going to check because they also have an account of all the transactions. If I'm an honest node and there has been a block that has been proposed, I'm going to check all its transactions if they match by or if they abide by my transactions. If that is the case, I'm going to take its hash and include it in the next block that I may be, I may be nominated to propose. Right, but if I think this is an invalid, I'm just going to ignore this block. Makes sense? So in a sense, trust isn't placed on the proposer, it is placed on the verification. And a block lives only if every transaction inside it checks out. Makes sense? Coming to the next slide, why the consensus algorithm works. So let's see how a malicious adversary could try to subvert this process. We will just have to now think like an attacker. So what can I, as an attacker, say Alice, just try to do to cheat the system? First thing I can do is steal the bitcoins that belong to another user. She's not able to do this because she cannot forge someone else's signature. Now what? After you have written all your transactions into a block, you have to sign it with your signature, right? So what happens? Stealing coins directly, it becomes impossible because of this. Because every Bitcoin transaction requires the owner's digital signature. And without it, Alice has no cryptographic way to pretend that those coins that she's signing belongs to her. Makes sense? So I cannot steal the bitcoins that belong to another user because I need their digital signature. Then second way by which she can harm the blockchain is act against another user, Bob. Now think of it, I am a fraudulent user, but I know Bob is an honest user. So whatever block Bob proposes, I'll just say I'm just going to ignore it and I'll not insert it into my blocks, right? So what I'm trying to do is just see the example what they've given. Alice could try not to insert any of the Bob's transactions into the new blocks. So what I'm trying to do is I'm trying to censor Bob by ignoring his transactions by mentioning in the chain that I think Bob's transactions are invalid, they're fraudulent. But the thing is, network is not going to rely on me. There are another honest nodes that are present in the chain, and they are going to validate Bob's transactions. And if he is an honest node, they are going to take his block and append into theirs. Right? Oh, so Alice, Alice has got great minds, but she cannot just go in and just harm the blockchain. So what she will do next is the last thing that she can try to do is try to spend some coins twice, double spending attack. So here it's not the money, it's not the physical currency that I'm using, right? I have data which I am using to buy something, to to have this transactions done. So it's data. Now let's say I am Alice and I want to transact with Bob. I transacted with Bob, I gave him my coins, and this was noted on the transaction chain. But then I am a malice user. I am a fraudulent user. What I'm going to do, I'll keep those data copied, because what is coins? It's just data on the internet, right? I'm going to keep a copy of the data that I have actually sent to Bob, and that same data coins I will send to Charlie, let's say. So this is double spending. With the same coins I'm trying to do two transactions, right? So Alice is trying to do what? I am trying to do what? To send the same coin in two different transactions. But you know what? The consensus algorithms that we have without a central authority, they're going to ensure that only one version survives. Either this transaction will be taken as valid or this transaction is going to be taken as valid. Both the transactions are not going to be taken valid in the same go with the same coins actually. So what the nodes are going to do, they're going to accept the first valid transaction that is going to be recorded in the chain, and the conflicting one with the same coins, it is going to get rejected. So let's see what can a malicious node do. So what can your malicious node do? So you have the block getting built one on one. After the first block, you had another block. Then you have another block in which you see a transaction where your Alice coins from Alice are going to your Bob. Makes sense, everybody, right? This is true. Okay. Because I have sent some coins to Bob, and that is correct. Now this is signed by Alice. That says pay to pay to your B, pay to Bob. Then what? And this has an hash for the entire blockchain. You remember Merkle root? It gives you the entire blockchain's hash. And then I add in another block saying that these are the same coins that I'm going to give to Alice. Right, and this is again signed by me, again has the blocks, again has the blockchain's Merkle root. And now this is called double spending attack, because I'm using the same coins to pay to Alice, to pay to Bob at the same, to pay to Charlie, or let's say A dash is your Charlie, to pay to Charlie and to pay to Bob at the same time. And that is wrong because I'm using the same coins. It's called double spending attack. So what your honest nodes, now honest nodes will extend the longest valid branch that you'll see in the next upcoming slide, right? So what is going to happen? Now I have this transaction that is a fraudulent transaction, that is me paying with the same coins that I've already used for Bob to Charlie. So now this is a fraudulent transaction because I've already used those coins to pay to Bob, and now I'm trying to use those same coins to pay to Charlie, to have transaction with Charlie. That is fraudulent. So what I do, I just keep extending this blockchain. I just keep, building blocks on it. Now it becomes the longer blockchain. Oh, sorry. So it becomes a longer blockchain. Right. Now I broadcast this to the network. The network sees this as the longest valid branch because no transaction was built over the block in which the transaction that I paid to Bob was recorded. But the blocks were built on the transaction where I said I paid the coins to Charlie, A dash. So this branch gets longer, right? So what my honest nodes are going to do? They're going to build on this. So more. morally it is wrong because I paid first to Bob and that should have been a valid transaction. But because this chain got longer, I tried to actually cheat on with the system. So now this transaction, this part of the chain from where we have a record that I paid to Charlie, this gets longer. So all my honest nodes are going to come in and say this one is the longer. It is not going to harm the system. Actually, the double spending attack is not going to work because now the transaction that I paid to Bob is going to be invalidated, which is morally wrong because I genuinely paid to Bob first and that should have been the right transaction. But this transaction is going to take its place, though the double spending attack is going to be ignored. So from Bob, he hears about the transaction that Alice to Bob, and right now he has zero confirmations, right? Nobody has confirmed that block. Then he gets one confirmation. And then there is a double spend attempt. The same coins, the person Alice, she tries to pay in with using the same coins to Charlie now. So then the confirmations increase, and heuristically what we say, if we have 6 confirmations on a block, we consider it to be valid, and then start building blockchain around that block, above that block, right? So then the double spend probability decreases exponentially with the number of confirmations. So now this actual transaction that was wrong is going to be considered fraudulent, is going to be ignored, invalidated. So with this, protection against invalid transactions is cryptographic but enforced by consensus. Are you getting it? There are transactions that do not follow the rules of the system, that is like double spending attempt, trying to spend more coins than available. It is different. Trying to spend more coins than available. These are the invalid transactions. So cryptographic mechanisms, let's say your digital signatures, let's say your blocks hash function, let's say your entire chains hash function, they ensure that only the owner of the coins can sign up a valid transaction, so that the transactions, they cannot be tampered with. But whether a transaction is accepted into the blockchain and agreed upon by the network is determined by the consensus rules, the rules that say, okay, we all agree, or 51% of the network agrees that this block is valid and it can be appended next to the blockchain, right? Then comes protection against your double spending is purely done by consensus. So unlike your validation of individual transactions, double spending, this is all these is a system level problem. Consensus protocol prevents double spends by deciding which chain is accepted as the main chain. A block deep in the longest valid chain is more likely to be part of consensus. There is no cryptographic guarantee though that the transaction is final. It's only a probabilistic guarantee based on the number of confirmations. Are you getting it? But we assume that we have a larger number of honest nodes in the network to determine that we only add honest blocks into our blockchain. Then the next line that says, you are never 100% sure a transaction is in consensus branch. Guarantee is probabilistic. So after a transaction is broadcast, the chances that it gets reversed decreases exponentially as new blocks are added on top of it. Heuristically, we say that if we have 6 confirmations, the chance of a successful double spend is negligible in most cases, right? So with this, next we're going to come up with Byzantine's agreement, and that I believe is a little more trickier part, little more part where you're going to get where you have to employ all your brains into it, and that is what you're going to actually like. It is a little thrill part of the blockchain series yet that we've seen. So yeah, if you have any doubts, if you have any concerns, please use the comment section. And also you can post it in the Google Forms as well if you want some reclarification on something already taught, or if you want me to take up another subject, anything that you have in your mind. And if you found the video helpful, just go in, like the video and subscribe to the playlist. Thank you everyone. Bye bye.